In this video, I want to go through some of the best practices that you can create indexes with so that you can gain the best performance for your queries. I'm going to execute 4 different queries on this beautiful table that I have here. I have a table with 3 integers, A, B, and C, and I'm going to play with the indexes on A and B. So I'm going to create a configuration where I have an index on both A and B. I'm going to create a configuration where I have a composite index on A and B, and I'm going to create a different kind of configuration where I have a composite index and a normal index on B. All right, and I'm going to execute the following queries where I'm going to query only on A, and I'm going to query only on B, and I'm going to query A and B and query on A or B, because that's most of the stuff that we do on the back end. We query with these particular filters. I understand we have end statements, we have other kind of aggregates, but we'll take it step by step. I hope you learned something useful with this video. With that said, let's just jump into this and play with this thing. All right, guys. So let's start with creating an index on A and another index on B. So I'm going to create an index on test A. By the way, I think I have around 12 million rows in this table. Not much, but enough for us to experiment with. So I'm going to create another index on B. All right, all done. Let's test. So we have an index on A and an index on B. So let's check our queries. So the first query I want to do is select C from test where A is equal 70. And I'm going to prefix this with explain and analyze. That will tell us how much the analyze took and the plan that has been used in order to do this thing. How about you jump into it? Do it. Fast. Fasto this. Very fasto. All right, so what happened? Obviously, the Postgres decided to use the index. However, it created a bitmap in order to query this index because there are a lot of rows. Look at how many rows. We have 9,000 rows. So it has to create a bitmap. Why? Because we have to jump back to the heap to pull C. C is not in the index. C is not included in the index. So we have to jump back to the heap to pull the value of C, right? After locating that. So we are building a map of all the values, the row, the tuples, in order to jump back to the table and pull that. And that explains why we have a bitmap index scanning the index itself that we just created on A. And then we jump back to the heap to actually pull those rows. And we have a cost, took 253 milliseconds, not that bad. All right, so that's what we have done. And what I want to do here, I'm show you that we can easily change this, kind of infer the decision of Postgres by actually limiting the number of queries. So if I say, okay, give me only 2 queries back, 2 rows back, look what Postgres decided to do. Because we have only 2 rows came back, Postgres doesn't need to take the overhead to build a bitmap, because building a bitmap takes a little bit of time, right? You have to compile this structure, you have to come up with all values, but it says, oh, I only found 2 rows, I don't need to build a bitmap. So I decided to do an index scan, a clean index scan, especially that these rows are contiguous, they are ordered, they are sorted. So the values that I'm gonna get, I don't need a map for this. I just can go pull those values directly from the heap. All right. So we use the index. How about to go to the other query? My other query is B is equal 100. So still pulling C, where B is equal 100. Let's take a look. So it took 250 milliseconds. We also use the index. This time we use the B index because, yeah, I'm querying on B. Naturally, I'm going to use the index on B. And then I hit the table directly with a heap scan using the values that I picked up from B. All right. Usually this is also a bad idea, right? Because you're not going to pull 10,000 rows. What are you going to do with 10,000 rows? And unless you're doing some sort of aggregate, that's a different story. But all right. So we have the value. So we're using the index. All right. So let's do this, the query now, but we're going to query on both A and B. So I'm going to do A equal, 100 and B is equal 200. Let's see what Postgres decides. So now we're going to do an AND between those squares. So Postgres decides, okay, in parallel, I'm going to scan the A index, I'm going to scan the B index because you gave me two values, right? And scanning those two values, I'm going to scan them and I'm going to build a bitmap, right? And literally you get a bitmap and then literally just AND those bitmaps. You're going to end up with a certain values, right? Some values will zero up, some values won't. And then you're going to end up with a set of tuples that you're going to hit the heap and pull the table directly. And that's extremely fast, right? As you can see, it's just happened is like how many values did you really return, right? We returned 6 rows. That's why it's pretty fast. And the ANDing operation is extremely fast as well. So that's what Postgres do in case of an AND. Let's try an OR. What would an OR do? I'm just going to change this to an OR. Boo! With an OR, it took obviously longer, and that explains a lot, obviously, because OR always brings more rows than AND, right? And now we did exactly the same. We scanned this index, we scanned this index, we brought the bitmap, we ORed them, got a lot more rows than we wanted, and then we got back the results. So pay attention to what this really happened, right? We're doing double the work. We're doing scanning this index, scanning index, and going to the table, giving it these rows, and then going to the table to pull these rows. All right. So now I'm gonna drop these suckers and I create a composite index instead. Let's do that. Test the A, IDX, test the B. All right, both the indexes dropped. Now what I'm gonna do is create an index on test AB. So this is a composite index, a little bit different, right? So we have one index that have both values. So it's going to take longer to create, and it's going to be more efficient for queries that have both A and B, especially the AND cases, right? Because the AND cases, we did a lot of work. And guys, don't pay attention to the values that how long it took, because this is really depends on the machine, depends on so many things. I want you to pay attention to how much work Postgres do, and that's what I'm explaining essentially. All right, let's do the first query on this. So now I'm gonna only query against A, and let's see what we're gonna do. Look at that. Actually, Postgres decided to use the AB index despite me querying on A. Why? Because A was on the left-hand side when I created that, and that matters. Because it's on the left-hand side, the values can be easily scanned. That's the Postgres rule. You can scan the values from the left, but you cannot scan them from right. Just the index are built left to right, right? And when you build that query, the index decided to use, the Postgres decided to use the index and then jump back to the heap, right? So it took 250 milliseconds to find all those values, right? And I believe if I do a limit, let's say limit 10, as you can see, it's an index scan instead of a bitmap. So it's like a little bit faster. All right, let's do the B. What do Postgres do when I do a B? 100. Ooh, you felt that, huh? It's a parallel sequence scan. Why? Postgres will not use the index. Why? Because you cannot use this composite index when you're scanning a filter that is not the left-hand side. It's either A and B or A. You cannot use B. So be very careful. So if you have a composite index on A and B, querying on B will not use the index. So what the table does, what Postgres does is just jump directly to the table and does a full table scan, and using multiple worker threads to do that, right? So it's obviously very, very slow. So very careful. Be very careful for that. All right. What happens if I do A and B? A equals 70 and B equal 80, whatever values. Look how fast this thing is. 0.5, half a millisecond. This is absolutely insane. That is the best case scenario. If you really all the time, if your queries are all the time like this, have a value and value, it's a great to create an index, composite index. If your application only does that, and hopefully only does that, and you're also querying an A, best case scenario is to create a composite index. Yeah, it's more costly to create a composite index compared to a single index because it stores more values, obviously, right? But the performance is remarkable, right? All right, how about OR? How about OR this? OR this ka? Oh, nope. Or in OR, all bets are off. You cannot use any of the indexes, right? I mean, Postgres decided in this case it's useless for me to query and try to use that because, like, you know what, might be faster for me just to go and jump to the table scan, do a full table scan instead. So that's what Postgres did, and Postgres does. Most databases do all these decisions on behalf of us, right? So, okay, maybe it's better to do this versus do this. I mean, if you look at this, it's like, okay, you have an index on A, you can query on A. I mean, you have an index on A and B, but you can query, you can use the index for A. But Postgres decided, no, you know what? It's way slower. I'm going to do this. I'm going to do a bitmap and then go for B. I don't have an index. So anyway, I have to go jump there and do the full scan anyway, right? What happened if I do a limit? Limit 1, sequential scan on this. It's not even parallel, it's just sequential because we know we're going to pull only first row. That's fast, and that's directly on the heap. All right, guys, the final thing we want to do is we know that B suffered. Queries on B suffered when I have a composite index. So what I'm going to do here is show you that I have a composite index on A and B. What I'm going to do is create an index on test B in addition to this index, and then execute the same queries again and see how things are doing. All right, so what will happen now if I query on A? We saw this because we're going to use the composite index. That's fine, that's fast, right? That's nice, right? How about if I use B? If I use B now, we're going to use your beautiful index that you just created for us. So that's kind of a compromise as a backend engineer, as your database engineer. You're going to say, okay, some queries, I'm going to use the B to query this. So I might need an index there, right? So you're going to create an index in this case to speed up these queries, right? And then obviously we're going to hit the table and the heap in order to do that. All right. Let's do A and B. A and B. Absolutely genius and fast. Look at this. Right? We're going to use the composite index because of the B, right? Right? How about A or B? Or now that we have an index on B and an index on AB, now Postgres is, oh, wait a second. Actually, we have an index on B. I can query the index on B, build a bitmap, and then I can query. Since we're querying on A, I can still use the composite index because it's a left-hand side. I can use the query and the index on that, build my bitmap, beautiful bitmap, build a single bitmap, jump to the heap, and then pull the rows that I want. All right, guys, that was some of the best practices that you can do to work with indexes, right? This is just some of them, right, guys? Sometimes indexes can shoot you in the foot. Sometimes they are great, but just learn how to use them. I can't possibly in 10 minutes explain all possible combinations, but hopefully this helps you kind of understand what the database is doing when you are actually querying the indexes. This is very, very critical as a backend engineer. This is one of the skill set that you have to put in your belt when you're building database applications, essentially. Hope you enjoyed this video. Give it a like if you like it. Give it a dislike if you don't like it. I'm going to see you in the next one. You guys stay awesome. Goodbye.